I would like to introduce Stephen March from Iowa State, who worked at UT Austin on electrical and optical studies of metal semiconductor nanocomposites for nanophotonics.
Thank you, Dr. Deal, and good morning, everyone. So my study focused on the characterization of optically tunable 3-5 semiconductors for a focus on different engineering applications, and the insight provided from this investigation sheds new light on different optical applications and the materials and how you can use them. So starting with a brief motivation of how we are looking at this project, there are several optically tunable 3-5 materials, and the applications we're interested in are infrared as well as fiber optic sensors and plasmonics too. So growth techniques we're using for this particular project, the main one is molecular beam epitaxy. And this is a fantastic technique because it allows you to have atomic control over your growth as well as create different materials with really exact composition. So a sample of how a growth would work with an arsenic, erbium, and gallium system, you'd start with a substrate wafer. In our case, we're looking at gallium arsenide wafer. You start by depositing different epitaxial layers where you can focus on the individual epi layers as well as the individual atoms. You continue this growth process where you go one atomic layer at a time such that you create the exact composition that you want. And there are two main kinds of growths we're considering in this study. The first is the superlattice, which is an altering sandwiched layer effect, as you see here. And the other one is a thin film semiconductor. So specific project goals we're dealing with, the first is to investigate the optical tunability of rare earth mononuclide nanoparticle superlattices. Sorry, it's a really big mouthful. Where you're dealing with your rare earth materials and your mononuclides, so referring to your group 5 elements. The second is to say the bursting Moss blue shift and the electronic band structure for heavily doped indium arsenide systems as a function of those different MBE growth techniques and different dopant types. The experimental setup I used, so starting with an optical setup, you have an illumination source, a series of mirrors, your sample as well as your detector, where you have light that comes out of your source, it hits your hits your sample, and once it hits your sample, that light can either be reflected or transmitted. In this case, you see, based on the blue line, your light is going to the detector, and that indicates that we're looking at a transmission measurement specifically, but we also did reflection measurements as well. And this detector, and our experimental setup was limited in that it could only detect a range of 3 different wavelengths. So we had 3 different curves collected in the lab view, but in order to make sense of those 3 different wavelength regimes and tie them all together to make a complete picture of a transmission or reflection spectrum, we had to first normalize those and then splice it together such that we had that complete spectrum from 800 nanometers out to 5,000 nanometers. Moving on to the results for those for the rare earth mononuclide nanoparticle superlattices first. So this is a TEM image of a gallium arsenide and erbium arsenide superlattice where you can see the individual nanoparticles up top. And as the specific things we could adjust, the rare earth material, the number of periods, period size, and the nanoparticle size. You can see the period length there, as well as, just altering the size of it and the number of periods involved. So first, this is a transmission spectrum looking at 3 different material systems, focusing on erbium, lanthanum, lutetium, as well as lutetium. As you move from an erbium and lanthanum lutetium-based system with very small nanoparticles and a few number of periods, and you increase this down, or you move toward lutetium-based systems with larger nanoparticles and more periods, you see this dip in the transmission spectrum. And a dip in the transmission spectrum would indicate an increase in absorption, especially for these particular materials. And you notice that this dip happens around 0.8 electron volts, which is very near to 1550 nanometers. And this is extremely important for different fiber optic systems because this is a mature technology where various sensors rely on this 1550 nanometer value. So this shows us that by using these nanoparticle systems, we can actually make better sensors or sensors that are well tuned for different fiber optic systems. And the discussion of how this would work, if you started off with an intrinsic gallium arsenide material and you sent in a low energy photon, you wouldn't have enough energy to overcome the band gap between the conduction, or between the valence band and the conduction band. However, when you add in these rare earth nanoparticle superlattices, you create intermediate states between the valence band and the conduction band, such that if you send in that same low energy photon, you actually experience absorption. In essence, it's adding select amount of impurities to a system to increase its absorption characteristics. And with that, we're showing that we can selectively engineer how these materials operate. For the second project I work on with the heavily doped indium arsenide systems, we considered the absorption spectrum such that as we increased doping, we saw an increased amount of absorption. And this is consistent with the expected blue shift and the band gap. And as a function of doping, we see that the carrier concentration, or as a function of doping, the band gap increases. And we have a tunable range between 0.64 and 1.16 electron volts. And that's much larger than the 0.33 electron volt effective gap range. N-type materials were more responsive than P-type. And we saw this divergence towards non-parabolic behavior that we expected from different literature values. A brief explanation of how that works. As you move from an undoped material to a heavily doped material, you have the conduction band that starts filling up. And so these filled lower states in the conduction band such that with a low energy photon, an electron cannot experience promotion up to the conduction band. And if you send in a high energy photon, you can actually see that promotion up to the conduction band and you see absorption instead. And with that, you have this quantified difference where you have a new effective band gap, and we were looking at that non-parabolic region specifically. To conclude, we explored two different material systems, the rare earth mononictide and heavily doped indium arsenide systems, and we demonstrated that you can engineer these materials for sub or greater than absorption, or band gap absorption, controlled through MBE techniques. This is important because different optical and or different communication and sensor technology relies on the optical tunability of materials, and this provides new insight as to how we can engineer materials and enhance device performance. Are there any questions?
Questions?
Come on, guys.
Okay, I'll ask one.
Please.
Show the, go back a few slides to the spectrum for the different materials.
Which one?
Back, keep going. That one there.
Yeah.
So you see that trend. Can you explain why you get that? Did you say it for higher atomic number, it decreases, or what?
So, as you're looking at these systems, you definitely have, I guess you could think of it as increasing atomic number.
Yeah.
Lanthanum definitely lower, lutetium being higher, erbium, so on.
Right, okay.
But the reason that we see this particular trend and how we have an increased absorption, it deals with the crystal structure involved, where this erbium arsenide structure in the TEM image shown here, it bonds better with the gallium arsenide intermediate layers, such that it creates a better interface and you have a better electrical optical properties.
Okay.
Yeah.
Good.
Yeah. And just to mention, the lanthanum doesn't show that as well. Yeah. Good. So, to repeat the question, what are the applications of these, as an example, the erbium arsenide systems, like as I'm showing here? So, and your specific concern is if there's a decrease in transmission, wouldn't that be a concern because you want to transmit data? All right. So, in this particular case, these are sensors such that you absorb an incoming signal and you can detect it. So, you actually want an increase in absorption that is a decrease in transmission, if that makes sense. Okay. Yeah.
What kind of detectors did you say?
So, as an example, with this system, you see a peak around 0.8 electron volts. So that would be better for fiber optic systems. But if the heavily doped indium arsenide materials, we can actually push out where the effective band gap is. So that would go towards shorter wavelength or higher energy materials. So it's just a matter of it. This project demonstrates that we can selectively engineer or tune these different materials for a wide array of different optical applications. Great question.
Good. Okay, thank you.
Yeah, thanks.